everybody, and welcome to the Learn It, Turn It, Burn It, Torque and Drag mini-series. I am so excited to be here with you guys. I am so jacked up. Today's episode is brought to you by NEWPARK. So thankful for our sponsors at NEWPARK for being a part of this. This is going to be an absolutely amazing session. I am getting so many emails and text messages and everything else. Like nobody else has any idea what I've got going on today. So first things first, guys, please let me know where you guys are watching from. So excited to have you guys all here with us. We're going to go through, we're going to do a basic little kind of intro, kind of like how we do on the Viewer Locksmith show. And we're going to do a quick little giveaway, which I completely forgot to set up. So I probably need to do that right now. StreamYard. That one. So much going on this morning. Hashtag NEWPARK. There's a clue for later. That's a good clue. Actually, there we go. Comments. There we go. All right. So now that's working. Then I got to get it put up on the screen. This is what happens when I go on vacation. So if some of you don't know, I went on vacation for a couple of days. I was in the Dominican Republic. My best friend got married. It was a great time. Really, really enjoyed it. The sand is beautiful. The weather was nice. The food was okay. It's all inclusive, so there's drinks. I don't really drink, so that really didn't matter. Anyways, hope all you also enjoyed the video that we did yesterday. That was a lot of fun that we made here at the back of the office. Big thanks to Rick Allen for allowing us to be able to shoot live here on his location. So we're looking for the Chrome tab tool. There we go. There we go. There we go. Share. Okay, now we got everything loaded up and ready to go. Once again, thank you guys so much for being here. This is the episode number 1 with Brandon Foster from TD Unlimited. Huge thanks to Brandon for helping me be able to put this together. A lot of this all stemmed from a post that we did, or a post that I did on LinkedIn back in, I want to say it was like August or September. I was looking for somebody to be able to come on the Viewer Locksmith show and talk about torque and drag. And it turns out that just doing one episode on the Viewer Locksmith show wasn't going to be enough to be able to talk about torque and drag, that there are so many parts to it. And this is a good chance for me to be able to learn about it. And I'm actually going to take notes today. Normally, I don't get to take notes during the show. I just have to be able to do the interview. So I'm really excited about this as well. As you guys could probably tell, energy level is much higher than normal. So anyway, so we did that post. Then I got in touch with Brandon afterwards and I said, hey, is there any way that you can help me put together maybe like a mini series or a conference or something? And so this is the birth of that idea. And we wanted to be able to put together a 7, and stay tuned for a little bit part later, a 7-part series that is fully educational for you, the audience, to be able to learn about torque and drag and not be pitched a software or a service at the end of the day. Right. So that's why we really think that, we're trying to change the game, trying to change the way we do things here. So that's where it came from. And then we reached out and we got a handful of sponsors. NEWPARK is our sponsor for today. Once again, thank you so much to those guys for being a part. All right. Let's go over and check. Be sure that if you guys are watching this, you can watch this. If you're having any troubles watching this, you can watch it on Facebook, YouTube, and LinkedIn. So if you're having any troubles on LinkedIn, there it is. If you see any links from somebody saying it's the official link and it's not from me, do not click on it. That is pure spam. Okay. Do not click on it. We had this problem with one of the last, with the managed pressure drilling event. So just stay away from them. All right. Let's check the comment section real quick. Holy wow. Lots going on here. Dr. C says, is he too early? No, you're too early for your presentation. Yours is in a couple of weeks, but you're not too early for the show. So we got Abdullah saying hi. Ian Hirsch saying hi from Woodlands, Texas. Always tuning in. Muhammad from Oliasoft. So his team's on next week. So be sure to tune in for that one. Alpesh, Jose, Eric is tuning in. Hello from sunny South France. Golly, I need to make it out there just to be able to see what his view is for the show, because obviously it's always sunny. He's never said rainy South France or anything. All right, Christopher tuning in from Richmond, Texas. We've got Iraq tuning in. Hello, Mr. John DeWart tuning in from Colorado. Great to see you here. huge thanks to Felipe tuning in from Brazil. He's been one of the show's biggest advocates there in South America, maybe even giving Rogerio at Pan America a run for his money. These two guys. Huge thanks to Salim tuning in from Algeria. Thanks for being here. Good buddy Artie Morrison tuning in from Magnolia. Thank you for being here. We've got Germany tuning in, Kuala Lumpur, Tarzan, Texas. Pete's in Tarzan. Well, Pete, thanks for being here. I do appreciate it. Sunil says hello. I mean, I'm going to click through these as quick as I can, guys. I wish I took more time to be able to do this, but if we did, we would not get through to the show, and we're already 7 minutes in. So just wanted to know live water hose demonstrations yet. Anxiously awaiting Norway. Can't do the live water hose on this one. For anybody that didn't see that, go check out the video I posted yesterday. I think it was kind of funny. Maybe we'll start doing some more David Explains It Terribly videos. Andrew Switzer student, hello from location of the Permian Basin AADE operator forum. So as soon as I finish this, I go back to the house, and then I get on the road, and I'm headed to Midland. And I will be at the AADE operator forum this evening. So if you can, you should be there. It's probably already sold out, but hey, tune in from Geneva, Jakarta, Iran, Houston, Perth, Norway, Iraq. Wow. Good gosh. Okay. All right. Let's start to move on with the show. Thank you all for tuning in. I really do appreciate it. Oh, hey, David. You got a great guest, best in the industry, in my opinion. Oh, see, look, there we go. Brandon's the best guest. This is a great question. Is there a possibility to watch it later on YouTube? You can watch it later on Facebook. You can watch it later on LinkedIn, and you can watch it later on YouTube. You can watch it on all three platforms. The easiest one to be able to find it afterwards is definitely going to be YouTube, right? LinkedIn does not do a good job of letting you find polls like content from previous days and stuff. So yes, the best way to be able to watch it later on is on YouTube. When we get done with the entire series, we're going to package them all together into one singular playlist, maybe even cut them down a little bit more. But it will all still live for free for as long as I've got the YouTube channel and nobody steals it away or buys me out and tells me to take it down or I get copyrighted or something like that. It will be there. So 100% free educational content that will live on forever. And that's why we have great sponsors like NEWPARK. Randy in the house. Thanks for being here, man. Dean, guys from Vermont. Thanks for being here. All right. Wow. China, Beijing, Colombia, Trinidad. Man, I am just blown away by the support for this event. And I know it's not me. It's all Brandon. You guys are not tuning in to see me. So special thanks to Brandon. All right. So let's take care of some quick housekeeping. So we're going to do a little giveaway. And I want to show you guys something. We're not giving away a little drill bit. This is a little one. Not giving away this. We're not giving away this size drill bit. No. We're giving away a big drill bit. Check that out. So if you want to win a big drill bit, let me do this real quick. Where's the little thing? Where did I find it? There it is. Type in hashtag NEWPARK into the comment section now for your chance to win a full size 8.5 inch with 4-inch regular threads Gibson Reports drill bit right there. Right. And it changes colors. Check that out. Right. Yeah. If you want to win one of these drill bits, do it. Right. And we'll play a little special. Like I've got a couple of these sitting here. Right. Oh gosh, almost dropped it. Let's see if we can get the other one. See, we got triplets. Yay. Okay. If you want to win one of these, type in hashtag NEWPARK into the comment section right now. We would really appreciate it. And so would NEWPARK. All right. Let me get these down before I start to break them. There we go. All right. And here is a quick word from today's sponsor. All right. And special thanks to NEWPARK for being the sponsor for today. So let me get that off the screen now and put that one back on. There we go. All right. Let's do the drawing real quick. Let's see how many people have entered in. 115 so far. There we go. That's what I'm talking about. All right. So let's do the drawing in 5, 4, 3, 2, 1. Boop. All right. Let's see who the lucky winner is for one of the. Now I'm talking about. So we're gonna do this again next week. So if you don't win this week, tune in next week. Dane is the winner. That's what I'm talking about. All right, Dane, thanks so much for tuning in. You just won yourself a drill bit, and it's not a DBR one either. Right. So there we go. All right, on with the show. Now, here for the moment of truth and for the amazing presentation. Welcome to the show, Mr. Brandon Foster. Brandon, thank you for being here, sir.
Thanks for having me.
Man,
fantastic.
This is going like light speed this morning. I have to ask you, what did you think of yesterday's video?
It was phenomenal. It's going to be a hard act to follow, though, especially given how cold it is in Montana. Danny Kane, I would go out and get a hose for a demonstration, but my hose is completely frozen. That's the advantage of shooting one of those videos in Austin and not in Montana in January.
Yeah, there we go.
Sorry.
All right, are you ready to be able to take on the, I don't know how many people we've got watching because I haven't even checked in to be able to see. Let's see. I think we've got over 200 people watching right now, plus another 4750 on YouTube. I highly doubt anybody's watching on Facebook. So yeah, guys, do us a favor. If you're enjoying this, tag somebody you like in the comment section, or share it on the social media platform of choice. Let some other people know that what we're doing here. So if you guys have any questions, what we're going to do during this was we're going to let Brandon go all the way through his presentation, and I will star any of the questions that we get so that we can save them for the end. And I guess now is best time as any to be able to give out the secret of today's show. This was Brandon's idea, not mine. We're going to do a second episode with Brandon at the very end of the series to wrap up and talk about lessons learned and answer any more questions that you might have after we've gone through the entire series of 7. So he's doing the introduction and I guess what we would call the closeout.
Wrap up. Conclusion, I mean, there's so much material we're covering here.
Yeah. So
no
there
doubt
will be a
we're
test.
all going to learn a lot.
If you don't pass the test, you'll never be able to look at a rig again. So there we go. All right, Brandon, I'm going to pop up your slides up onto the screen and let you take it away. Like, again, for anybody that, if you guys have any questions, just put them into the comment section. I'm going to star them, and then we will go through as many of those as we can until Brandon taps out and can't take any more.
Let's do it.
All right, Brandon, take it away, sir. Thanks for everybody for being here. And thank you to NEWPARK.
Okay. Well, I've got some kind of fancy animations in here that now in hindsight maybe have been a little overly clever that I don't know that they're going to work in this platform. So I'll do my best to adapt to that little change. But an agenda of what we'll cover here, a history lesson a little bit on torque and drag models, where they came from, and some good SP papers that you could go research if you want some more information. A little bit of the basics of the physics of how they work, although we've got somebody far more qualified than me to talk about that coming up in 2 weeks' time. And then a little bit of the application of how you actually use them and the sorts of problems that you can solve, a few of the mistakes that we see a lot in the industry, and then kind of some thoughts on what we could do better in the future. So let's go ahead and get started. A little bit of background on me. And again, here's where my animations kind of got screwed up. I'm a ranch kid originally, born in Montana. I've got 3 sons, been a drilling engineer for 23 years. So I guess when you've done something for over half your life, that's what you are. And I'll forever be a gearhead. In my mind, if you've watched the series Yellowstone, I still think that I'm that ranch kid, busting broncs and running around with cows. My kids, however, since they watched Armageddon, they think that every time we drill a well, we're going into outer space to blow up an asteroid. My mom, she's worried that every time we talk about drilling wells, that it's the Deepwater Horizon. I went to a rig in Oklahoma last year, and she got all clamped over the phone and asked me if that was in the ocean. And I told her, no, there's very little ocean in Oklahoma. And in reality, what my job entails is sitting at a computer and doing a lot of analysis. So that's kind of the reality of the situation. We're going to make a lot of analogies to mechanical things and working with tools. And this is our current pet project that I'm working on with my kids. It's an old 1980 GMC Jimmy. It's almost roadworthy, but lots of busted knuckles and 7 years of marital bliss with that sitting in the garage. If any of you have ever tore into a project like that, you know how those things tend to go. So we're almost there, almost across the finish line on the Jimmy. This is a slide, David, you've probably seen this before. It's the way I like to kick off a lot of talks. It's a little bit of recycled content. Everything else in here is brand new, but I like this because it frames a lot of what we're going to talk about, not just today, but for the whole 7-part series that we've outlined. And I learned about this from a geomechanics guy by the name of Tom Bratton. I don't know if he's on, but super sharp guy. If you're ever interested in geomechanics, he's the guy to talk to. But he referred me to a paper by Dave Herrick, and Dave was a petrophysicist at Mobile, which I didn't even know. That's where I started. I didn't know him at the time, but he wrote this paper, and you can find it online if you're interested. It's great. It doesn't have anything to do with torque and drag or drilling wells, but it's more of a philosophical take on the way humans approach problems. And the way he breaks it down is whether or not you use data or you use a model or you use both or you use none. And what he calls medicine or pharmaceuticals, I'm just going to call drugs, is an approach where you just use data. This is an empirically driven approach. And why he calls that pharmaceuticals, medicine, I'm going to call it drugs, is that's the way a lot of pharmaceutical companies develop their product, is with data. They do experiments on rodents, and then they move it up to bigger animals, and then they do experiments on humans, human trials, trying to assess the effectiveness of this particular product on a population. And once they've built up a significant of enough of a statistical database, then they've determined that it solves XYZ problem. You know, if your problem is heart palpitations, and if 90% of the time when you give the patient this drug, it solves the heart palpitations, then all right, it's good enough for human consumption. Totally empirically driven. They don't have a working model of every person's body, and that's why sometimes when you take XYZ drug, it doesn't solve the problem. Instead, it gives you explosive diarrhea. So, when you're watching news at night and you've got all these ads for the latest and greatest drugs and all the horrible side effects that might happen, that's because there's no model that says that this drug is going to work with your body. Religion, on the other hand, so that's an approach where you just have a model, but you don't have any data to support whether or not your model is actually correct. And that's why we have so many different religions around the world, and why we have world wars and brutal conflict, because nobody can prove with data that their particular view is right. And if everybody's got a different version of the afterlife, they can't all be right. So a model is very much religion. You're relying on faith that particular description is correct. A lot of young drilling engineers, same way. They have no experience, but they've got some software, run some calculations. You just have to take it on faith that those calculations are correct. Science, on the other hand, is where you combine data with a model. And that's how we manage to put satellites into orbit every single day. And that's how we know that the Earth is round. And that's how we understand gravity. So much human understanding has accelerated with the advent of science. So science is not just data. It's not just a model. It's coming up with a theory or a hypothesis or a way to calculate something, and then doing an experiment to see if the model indeed was able to predict what was going to happen. And the beauty of the scientific model is when the data is not consistent with what you calculated, that's a learning opportunity. That means either there's something else going on that's not explained by the model. It might also mean that the data is wrong, so we need further investigation to see if, okay, is there some problem with the way that we did our experiment? But a great opportunity exists for deeper learning if we use both data and a model. And when we talk about torque and drag, that's exactly the focus that I think we should have. Is you're not just taking a piece of software, calculating what the torque should be, you're taking advantage of all the EDR data that we have now when we drill a modern well to confirm that the input assumptions that we have are correct. And then that gives you confidence to project forward if something changes, if you change the drill string size, if you change your trajectory, if any variety of the input parameters change, that those projections are going to be correct. Politics, on the other hand, all of our favorite people are politicians, right? They don't use data or a model. They are making their decisions purely on their own self-interest. Now, in the oil field, we use all four of these methods on any given day. Sometimes you're going to pick a drill bit because that the superintendent's favorite drill bit color is green and you want to keep your job. So you're going to run a lot of green drill bits, whether the data supports that that's the best approach or not. Right. So we just have to be mindful that in any given situation, people are going to come at a problem one of these four different ways. And what I would encourage you to do is try to gravitate towards science. Science is going to give us better overall outcomes than drugs, religion, and politics. On the topic of drugs, right now, the data-driven approach or big data, that's a big buzzword in the industry. Everybody's really, they want to advertise that they're all about the data. What I hear when people say that they're focused on a data-driven approach is, I like drugs. And when they say big data, what I hear is, I like lots of drugs. So drugs, data in itself is not science. We need a model to supplement the data to get a deeper understanding. That's going to be a main message here. A little bit of vocabulary. One of them, we're going to mention friction a lot. So friction is just simply put the force that resists motion. And when we're talking about sliding friction, so two surfaces sliding across one another, it's very easy to calculate. The friction force is simply the coefficient of friction, this little Greek symbol mu, times the normal force. We'll talk about what the normal force is here in a minute, but this is a super simple equation. Couldn't be easier, right? Just two variables multiplied times each other gives you the force. The coefficient of friction is an empirical value. It's not anything that you can predict. You have to measure it empirically, and it defines the ratio of that friction force to normal force. So if you just rearrange this equation here, if you divide friction force by normal force, that's your coefficient of friction. And that's what we can do either with a torque and drag program or in a laboratory setting with a lubricity tester. We'll talk more about that here in a little bit. What is normal force exactly? Well, normal force is the force perpendicular to a surface. So if I know that the inclination of a surface perfectly perpendicular to it, that is the normal force. Tension or compression. That is the force acting along the axis of the string when we're talking about the context of torque and drag. Tension or compression is acting along the axis of our drill string. Torque is the force acting along the circumference of the drill string, resisting rotation. Somebody, I think, when Dave first announced that we were going to do this torque and drag mini series, I think it was Ray Proctor at Fernley Proctor said, "Well, there is no such thing as torque; it's just drag and drag." Because everything is drag, everything is sliding friction. That's true, but in the sense of drilling wells, what we call torque, turning the pipe, right, makes more sense to people than just calling it drag and drag, I think. Two other things that we're going to name drop quite a bit is soft string and stiff string. What is soft string? What is stiff? Soft string is a torque and drag model that assumes that the drill string is like a wet noodle and it follows the well path perfectly. The well path, at least as well as we understand it. Typically, we're surveying a well every stand or every 100 feet roughly. There's a lot going on between those survey points in most wells, but if we just assume that the well is connect the dots at each survey point, the drill string follows that path perfectly. Whereas a stiff string model is a little bit more mathematically complicated, and it takes into account the stiffness of the pipe and the fact that we're going to go across certain dog legs when we have a dip in inclination. And we're going to have additional side forces in certain places when we've got very stiff tubulars in a well path that has big dog legs. So those will cover most of the vocabulary terms that we're going to touch on, at least today. Little history lesson. The very beginnings of torque and drag models started in 1984. If you're only going to ever read one SP paper to better understand torque and drag, it would be this one, 11380. And it was written by three guys at Exxon at the time. Johansik, Rap Dawson. I didn't know Friesen and Johansik, but Rap Dawson was at Exxon when Mobil was acquired by Exxon. Great guy. And these guys were real scientists. They did some really neat stuff. If you read that paper, it's fascinating. They work out the physics of how to calculate the normal force, both in the straight part of the hole and in the part of the well that has curvature. And then because they were scientists, they didn't just rely on the math and the physics. They went out and developed sensors that you could put on the rig to measure tension accurately and to measure torque accurately. Now, remember, in 1984, very few rigs had top drives and a way to infer or measure torque. So they came up with these devices, a plate that you could drop into the rotary table that had a Wheatstone bridge to work out what the torque would be when your Kelly bushing's in the rotary table and you're drilling ahead with a Kelly. Awesome stuff, fascinating. But yeah, those guys are OG in my opinion, right? They set the groundwork for everything that came after. And if you want a real solid understanding of how the models work, that's the place to start. First bit of literature about a stiff string model was in 1988 with this paper. If you're interested in how stiff string models work, that's a good starting point. And then something else that we're not going to get into a lot today, but it's every bit as important as just pure torque and drag, and that's buckling of the string. There were several papers that came before this, but this is the one that I guess if I was going to tell somebody, if you wanted to, start from ground zero and build a working torque and drag model, this is the one that you would start with, SP 25503. A couple guys from Texas A&M, Wu and Yuckenwold. That, in my experience, has been a very reliable way to calculate when buckling occurs, both in straight well bores and in curving well bores. And the thing that's interesting about it is it also allows you to figure out what's often called post-buckling effects, meaning how much additional force is applied to the side of the hole once you throw the drill string into buckling. And if you saw David's video from yesterday, he got his garden hose starting to buckle on the ground, right, when he put enough compression on it. So that's a real important component of accurately predicting torque and drag is understanding buckling. Now, those three papers are not, the alpha and omega of torque and drag. There's been a ton of content published in the last 10, 20 years on torque and drag, and probably some of the most famous authors, Robert Mitchell, Robello Samuel over at Halliburton Landmark, Stefan Miska, professor in Oklahoma. One of the guests that's coming on, Stefan Manon, is published a great deal of material on the kind of monitoring and using actual data overlaid with models. Colin Mason from BP back in the 90s and early 2000s published a ton of content. So if you're really into this subject, those are the names that I'd recommend searching on OnePetro if you want to learn a little more. If you're like me and get bored with SB papers quickly, just start with this one. Some things about friction are a little bit counterintuitive. They surprised me when I learned about them years ago. And I think for most of us that work every day out on a rig, it would be surprising as well. One of the laws of friction is that the amount of friction force that's experienced is proportional to the normal force. So if you to help visualize some of this, if you think about a cinder block, if I've got one cinder block on the ground, let's say in my driveway of my garage, and I measure the force required to push it, that force will be exactly double if I take another cinder block of the exact same weight and makeup and stack it on top of the first cinder block, because I've doubled the normal force. Therefore, the force required to move it is also going to double. What that part is not that surprising. What doesn't seem right is that it doesn't depend on the contact area. And what that means is whether the cinder block is laying on this side or on the side that has the holes cut out, it takes exactly the same amount of force to move that cinder block across your garage floor. That doesn't sound right, right? Intuitively, you think, well, as I, reduce the contact area, it should be easier to slide, right? That's not how sliding friction works. And you don't have to take my word for it. This is a super easy experiment to do yourself in your garage, right? Just like your garden hose demonstration yesterday, David. This is something you can prove to yourself. The contact area is not what influences the friction. What does matter is the two surfaces that are in contact with each other. So trying to slide that cinder block on a chunk of rubber is going to take a lot more force than trying to slide that cinder block on a polished surface, let's say polished steel. Or if we put some sort of lubricant in between those two surfaces, that's going to change the force that's required to slide. In the context of drilling a well, what that means is your drill pipe sliding along cased hole is going to experience a different coefficient of friction than when your pipe is sliding out in the open hole across rock. Sliding across shale is going to be different than sliding across limestone or dolomite or sandstone. The other thing that's not real intuitive is that speed doesn't change how much friction is experienced by the object. So that means that if I were to move that cinder block across my yard at 10 foot, across my shop at 10 foot a minute or 20 foot a minute, it takes the exact same amount of force. It takes more power to move it at a higher speed, but it takes the same amount of force. If I had like a force gauge where I could measure exactly how hard I'm pushing on the object, it's exactly the same whether I'm moving at 10 foot a minute or 20 foot a minute. I skipped over this one, but static friction is always going to be higher than dynamic friction, which means it takes more force to get the object starting to move than it does to keep it moving. Those are 5 simple laws of sliding friction, and they are baked into every torque and drag program. So how do these models work? This is one of those little animations that is not working out for me this morning, so I apologize. The starting point is if every program breaks the string up into small pieces. Starting at the bottom, it'll break it up, usually in most cases, in 100-foot chunks. Now, if we have surveys at a higher frequency than 100 foot, or if we have components that are shorter than 100 foot, then in some cases, those pieces will be smaller, but in general, about 100-foot chunks. And then what it does is it basically does a free body diagram of your pipe and works out, depending on the inclination of the hole at that particular place, how much of the buoyed weight of any component is pushing into the side of the hole, the normal force, that end thing that we talked about, and how much of the weight is acting down the axis of the string. So if I was at 45 degrees, a certain percentage of that weight is going to be acting down the axis, and a certain percentage is going to go into the side of the hole. Just use a little bit of trigonometry to work that out. Then it will calculate the drag force just for that component. And all we have to do to calculate the drag force is coefficient of friction times normal force. And coefficient of friction is one of the inputs in the software. And we'll talk about this later. It's unfortunate that in a lot of software, that's just a single number. It implies, the way the software is set up, it implies that you should know what your coefficient of friction is. Well, we don't usually know what our coefficient of friction is. It's usually a range, not a single number. So sensitivity analysis is something that you're going to see more often with torque and drag calculations, because we don't always know, and it isn't constant. It does change as we drill the wells. We drill through different formations, as we circulate the hole clean, we remove cuttings from the well. So that's an aside. Sorry to get distracted there, but in essence, this is all it's doing is working out what is the drag force. When I'm pulling the drill string out of the hole, it adds the drag force to the tension of the string. If I'm running in the hole, if I'm slacking off, then it subtracts that drag force from the tension that's in that component. And then the next step, and it does all this, in milliseconds instantly, it will work out the torque required to rotate that 100-foot section of pipe. And in order to do that, all I need is the normal force, of course, the coefficient of friction, we talked about that. But for torque, I need to know the torque moment arm. And what does that mean? All I need is the radius between the center of the pipe and the surface that is touching the hole. And in most cases, that's your tool joint diameter. So if I've got a 7-inch tool joint, my moment arm is 3.5 inches. We don't work in inch pounds, we work in foot pounds. So I convert the inches to feet. And that's how I calculate torque to rotate that 100-foot section of pipe. So the computer does all this in milliseconds. Then it moves up to the next 100-foot section of pipe and the next 100-foot section of pipe from the bit all the way back to surface until you have a cumulative total load. And the way it's typically presented is this is the tension you'd have at surface. This is the torque you'd have at surface if you're rotating the drill string at this particular bit depth. Well, if you want to investigate a different bit depth. Let's say we want to drill 1,000 foot deeper in the hole. Well, it has to do all those calculations all over again. And that is why this is so much easier to do with a computer than it is by hand. Could you do torque and drag by hand? Absolutely. But it takes all day to get one little graph because you're having to do so many independent calculations. Let the computer do the hard work. A computer is a machine made for doing a lot of math really fast. So that's the basics of how it works. It's really not that mysterious and not that complicated. It's just a lot of math over and over and over and over again. Now, that is a simplification of what's going on. There are some things that make it a little bit more complicated, but for the basics of just understanding how the mechanics of it are working, I think that's an adequate explanation. There are some other things that create tension and compression or additional normal forces on the string. Some of them we can account for. Some of them are very difficult to account for or really can't be accounted for. The things that we can account for are fluid friction. So as you move the drill string up and down in the hole, you're also moving your drilling fluid. And depending on how thick the fluid is, how fast you're moving, earlier I said that it didn't matter how fast you're moving, but in the case of fluid friction, it does matter how fast you're moving. And how tight the clearance is between the pipe and the hole, there will be a certain amount of pressure that's pushing back on the string. So when we turn the pumps on, we'll see that our hook loads decrease a little bit. When we shut the pumps off, our hook loads increase a little bit, all because of this fluid friction effect. Likewise, when we run in and out of the hole. So that can be accounted for, and it requires that a full-blown hydraulics model be coupled to your torque and drag model if you want to account for those sorts of things. Back when I started my career in the early 90s, we didn't do that. We didn't couple hydraulics with torque and drag. Now that is becoming more and more common, and we're also kind of more aware. We understand how important it is that we actually do that. The other normal forces that arise are due to buckling, and I talked about that paper from Wu and Yuckham-Wold where they explain how you can calculate the additional side forces that result from buckling. In a soft string model, we kind of ignore bending, and in a lot of applications, most of the time, the bending effects are pretty minor and are negligible. In the original Dawson paper, they said the same. For the sort of clearances that we typically have, bending is not that big of a deal. General rule of thumb, once you start getting above 15 degree per 100 foot dog legs, then the bending effects start to become a little more important. Or, I would say when your clearances start getting very, very tight, when you've got big pipe and a small hole with big dog legs, that's where bending starts to become important. Then there's all the stuff we can't account for. So the complicated part is you don't know how thick the cuttings bed is. And if you think about all those little tool joints being drug in and out of the hole every time you move the pipe up and down, that adds a certain component to drag. What the makeup of the cuttings bed is also influences the drag that you perceive. The tortuosity that's in the hole, and I'm not talking about the tortuosity that you can see. We can see from survey point to survey point. What you can't see is in between the survey points. We're getting better at that now with continuous inclination, continuous azimuth, but we're not usually using that in a torque and drag analysis foot by foot to characterize the true trajectory of the hole. But microtortuosity affects the resistance to the string moving in and out of the hole. So does any differential sticking effects that might be present. Those things, because they're very hard to account for, get lumped into what we call the friction factor instead of the pure coefficient of friction. Coefficient of friction is something that you can measure in a laboratory setting. If you call up your mud company and say, hey, what's the lubricity of my fluid? They can measure that in a laboratory. It's going to be different out in the field. It is almost always, I've never seen a case yet where it's lower. It's almost always higher in the field than what we measure in the laboratory because there's a bunch of stuff that gets lumped in that we just can't break out, at least we can't in 2023, separate it from what we measure in the laboratory. Okay, typical output. And unfortunately, here's another place where my fancy animations are going to be a disservice. There's a bunch of layers here that you're not going to get to see. So if anybody's interested, I can send you the slides and you can see the animations that are buried behind this. But the typical output, what we're looking at here from a torque and drag program, we've got depth on the y-axis. And this is a real well that we're drilling in Mississippi right now, 7,000 feet down to 13,000 feet. It's not super long. It's not super complicated. This is kind of to illustrate that you don't have to be drilling a 40,000 foot record ERD well to use torque and drag. And the way that this is presented is, what would the driller see when he's running in the hole? That's the blue curves, what we call slacking off. Or when he's pulling out, we call picking up. The red curves are pulling out of the hole. The blue curves are running in the hole at a fixed speed without rotation. So running in, pulling out. The green curve, what's often labeled as Rob. Everybody, that's probably one of the most common questions I get. What is Rob? Who's Rob? I don't know a Rob. Rob is rotating off bottom. When the string is stationary, it's not moving in and out. We're just rotating in one place, off bottom. We don't have the bit interacting with the hole, bottom of the hole. That's the weight that we should see. It's also sometimes called neutral weight. The reason why there's 5 different slack off curves and 5 different pickup curves is we've done a sensitivity to different levels of friction, from as low as 0.2, so this is the 0.2 curve, to as high as 0.4 up here. In this area, in this field, we're drilling chalk with water-based mud. Chalk and water-based mud tend to be a pretty high friction environment. Remember earlier when I said that 2 surfaces sliding together matters. When you've got steel drill pipe in chalk with water-based mud, that's pretty high friction. In oil-based mud, I would probably choose a narrower range of friction here. Be more common to run it from, say, 0.1 to 0.3, with 0.2 being more common. Nevertheless, how you interpret this is, if I wanted to run the drill string all the way to bottom in this wellbore, what these curves are telling me is that as long as my friction is no more than 0.3, the drill string will slide to bottom. If I have any more than 0.3 friction, the string doesn't go to bottom, because this black vertical line is my block weight. If I follow this curve here, I run out of weight at about 11,600 feet. And that's due to helical buckling of the string. You don't know that just by looking at the graph, but later on in this series, we'll dive deeper into how you would know that it's buckling that's causing that to happen. That has a pretty significant impact on the operation if I'm drilling with a conventional motor, or if back in the day I didn't have a top drive. So when I first started with mobile, we were drilling all kinds of horizontal wells all over the world, but particularly in Texas. Go ahead, Dave.
Brent, I just noticed I can share on my screen so that we can do the animations. If you'll just tell me when to click,
Oh,
then I can
fantastic.
get it on. So
I think that would be helpful.
So add to stream. There we go. So I'm on this one. So if you'll just tell me when to click,
Yeah, click.
then let's go.
Yeah. Okay. We'll start with that.
Okay.
Perfect. I'll let you know.
All right. I'll take myself back off, and then you just yell a click or clap or something like that.
Okay. I'll call for the orange glasses when I need it.
Okay.
Okay. So as I was saying, back at mobile, we're doing a lot of horizontal wells. This was late 90s. Top drives were not that common back then. So most of the wells that we were drilling were with Kelly rigs. Exxon took over from Mobil. Exxon was drilling much more complicated extended reach wells, was very much on board with top drives. They were encouraging us to run top drives on all the old heritage Mobil rigs. And of course, being the small company that got bought by a bigger company, and we had all these, grumpy, grouchy superintendents and engineers and company men, absolutely awesome guys. But, our modus operandi at the time was resist everything that Exxon told you to do, right? So our attitude was, well, Mobil drilled all them wells with the Kelly rigs. We don't need no top drive. So we're in this field where Mobil drilled a ton of wells, but we had extended the laterals out 2,000 feet longer than what Mobil had ever done in this particular field, just south of Midland. And so we told Exxon management, we don't need no stinking top drive, right? Well, lo and behold, we're out there about 1,000 foot from TD, and the company man calls up the drilling engineer, it was me, says, Brandon, I can't get the bushings in the rotary table. I had no idea what he was talking about. I was like, what do you mean you can't? I thought he was having a personal problem, right? Fighting with his wife, or what is he talking about? Well, the drilling engineer didn't do any torque and drag modeling and wasn't aware that there's a very big difference between drilling a well to this depth and drilling a well to this depth. When this is the normal friction that you've got, here you can drill to TD, here you can't because of buckling of the string. With a top drive, it's not a big deal because you just kick in the rotary and rotate down and you're off to the races. But with a Kelly, it makes a very big difference. So we had to spend a lot of money on lubricant to get our friction to a lower level where the string could run in the hole. So that was an early lesson I had learned about, don't assume just because you've done a bunch of one thing in a field that doing something a little bit different is going to give you the same results. Back to our graph. So that's how you'd interpret slacking off. On the right, pulling out, got a range of friction factors there. And as long as the pickup weight is below the tensile strength of your pipe, you don't really have a problem. As soon as the pickup weight exceeds the tensile strength of your pipe, now you have a problem. So on one of the LinkedIn conversations, we're talking about, torque and drag problems. What is a torque and drag problem? Well, when you can't run in the hole, or you can't pull out of the hole, or you can't rotate, that's what most people consider a problem. But until you can't do what you want to do, is it really a problem? So that's why on these charts, it's very helpful to have your limitations overlaid with your load. We want to know both the load and the limitation. What limits you from running in the hole is your block weight. What limits you from pulling out of the hole is your pipe tension, typically. Now, sometimes when we've got an undersized rig, it might be the hoisting capacity of the rig. So you might overlay your maximum hoisting capacity. On the right, what I'm showing is a torque chart. We've calculated the off-bottom torque when I'm just rotating the drill string off-bottom.
Brandon, am I on the right screen?
I think so. What did I say that doesn't make sense?
Because I'm just making sure, because I'm still on the very first one. The very first.
Yep. Oh, go back.
Okay. I'm just making sure.
No, you're perfect.
Okay. Yeah.
Just like
I'm
mom
not perfect, but
no.
Okay.
Your mom was right. You're doing great.
All right. Just making sure. Keep going.
Yeah. No, you're doing great. Torque chart. For a range of different friction factors, that's the torque that we would see when we're rotating the string off bottom. I just kind of made up a limit there. In this particular case, we've got XT39. We can rotate up to 20,000 foot-pounds of torque. But imagine that you didn't have high torque pipe. Well, it'd be quite useful to know what is the maximum torque that you can go to, because once you exceed that, you can't rotate anymore. That's a real problem. So if I'm calculating this ahead of time and then in real time overlaying the actual torque, I can see what direction I'm headed. I can see what sort of friction I'm attracting, and I can predict quite accurately what's the maximum depth I can go to before I need to do something different, either run higher torque pipe or increase my lubricant concentration and look at other things that I could do uphole with my trajectory to try to reduce the torque. Okay, that's the most basic output you're probably going to see from almost every software. That's the way torque and drag is usually presented. David, if you would click one more time, what I'm going to show you now is what it would look like if I added a small amount of rotation to tripping in the hole and tripping out of the hole. Previously, what we were looking at is just pure axial motion. I'm running in, I'm pulling out. One of the things about friction is that it acts opposite to the direction of motion. When I'm running in the hole, friction's acting in the opposite direction, up hole. It reduces tension. When I ream, I'm actually moving the string in two directions. I'm going in the hole and I'm rotating, so I've got some amount of torque. How much of the total friction, there's a fixed amount of total friction. What percentage of the total friction acts along the axis? And what percentage of that total friction acts around the circumference depends on the relative speed of my axial motion and my rotational motion. So what we'll see here is sensitivity to how fast I'm rotating. If I'm running in the hole or pulling out of the hole at 100 foot a minute, 1 minute a stand, and I'm only turning the top drive 30 RPM with 4-inch drill pipe, if you just toggle back and forth, David, the point I'm trying to illustrate here is we get a little bit of drag reduction when I go from no rotation to now 30 RPM rotation. But if I go one slide further, David, to 60 RPM, you can see the direction that everything's moving. I've got less and less drag, but more and more torque the faster I turn. So go one more to 90 RPM. There you go. You can see how the drag curves are collapsing on that green line. If I've got very high rotational speed, circumferential speed, and very little axial speed, my drag essentially disappears, and what I'm creating instead is torque. It is a load sharing arrangement. I'm removing drag in favor of torque. This is the beauty of top drives and rotary steerable tools. You can make your drag go away if you rotate fast enough and or run in the hole slow enough, provided that you have enough torque capacity. So in the 90s and early 2000s, it was all the rage for all the drill pipe companies to come up with the next new high torque connection, because we began relying more and more and more on rotation to solve our problems. And rotation solves a ton of problems. We don't even need to talk about hole cleaning, all the side effects of that. But from a torque and drag standpoint, if you can rotate, you can make a lot of your problems go away. That's what we're trying to illustrate here. This concept is called friction vectoring, and it's something that Dr. C is going to talk about when we get it deeper into the physics presentation here in a couple of weeks. But I just wanted to illustrate this important point because I think it's interesting. If you're an engineer, it's like, that's one of those things that makes you go, okay, I do need to know that. Next slide, if you don't mind, Dave. If we go back to the no rotation, if I'm just picking up, slacking off, in real time, what I can do to get a sense of what's going on with my hole condition is plot actual pickup and slack off weight. And this is something that we do tend to do pretty routinely on ERD wells, but we don't do so much anymore on your run-of-the-mill U.S. land wells. So I just made up some data here because, quite frankly, in Mississippi, we're not doing this. We're not going to the effort of picking up and slacking off the drill string on every connection. But if I was, what I would hope to see is the measured slack off and the measured pickup following one of those lines. I don't really care which line it is. I just want to see that it's following one of those trend lines. If you click one more time there, David, what would be concerning is if I was following a line for a certain period of time, and then all of a sudden it started crossing lines, and we call this thumbs out. If the slack off is starting to get lower faster than it was, and the pickup is starting to get higher faster than it was, that's an indication that something's changed with my hole condition. It might be that I have a cuttings bed that's getting thicker. It might be that I've drilled into a zone that's unstable. In our case here, we've got this midway shale that's right above the reservoir that's extremely unstable with low density water-based mud. If we get into it, this is exactly what we'd see. Now, if you make whatever that problem happens to be that you got into go away, let's say we stop and circulate, and all of a sudden the drag trends go back to where they were before, then you know exactly what it was that caused the problem. If I stop and circulate and it gets better, then that was hole cleaning. Wellbore stability doesn't just all of a sudden get better because I circulated for 30 minutes. Hole cleaning will. So there's some real-time diagnostics that you can do if you've got the model and the data. Okay, so this is what we would call science, which our old buddy at Dave Herrick over at Mobile would call this science. Prior to putting the data on top of the charts, it's religion. We're just praying that this is right. But when you've got the actual measurement, now we're doing science. Now, if I took the theoretical charts away, I'm on drugs. All I'm doing is looking at the drag, and I don't really know what normal is supposed to look like. So you got to have both. If you combine the model and the data, you're doing science. If you separate one of those two out, then you're doing something that's not science. If you want to go one more click, David, I'm going to look over here at torque. Torque, common misconception is that it tells you something about hole cleaning, and it really doesn't. And that's because when you're rotating the pipe, you're not interacting with the cuttings bed in the same way that you are when you're picking up and slacking off. Now, this is actual data from our field in Mississippi. And you'll notice that the actual data, when I'm rotating the pipe off bottom, is kind of following that middle 0.3 friction factor curve. And we did a little experiment there. We had drilled out with 3% lubricant concentration in our water-based mud. We were kind of cussing and discussing, is this lube really doing anything? I don't know if it really is. Let's stop adding lube. Well, our lube concentration slowly drifts down to 1.5%. And you can see there, like around 11,000 feet, the friction comes up to 0.35. Huh. Well, that's interesting. I wonder if that's a coincidence, or is that actually because of our lubricant concentration? So we start putting the lube back in, and sure enough, it comes back down to a 0.3 friction factor. So we're able to quantify exactly what benefit we get going from 1.5% lube concentration to 3% lube concentration. And in some wells, it won't matter. Maybe we don't, if the lateral short enough, we don't need to run any lube. If we're running a long lateral, well, we can predict here, can we get to TD with 1.5%, 2%, 3%? How much is it that we actually need? Because it does start to add up after a while, depending on how much lube you're putting in there in terms of dollars spent. One more interesting thing, if you can click for me one more time there, David. This is, again, made up data, but it's to illustrate a point. And what we use static torque for, if you think about making connections when you're drilling a well, drill Kelly down, the first thing that you do after that pipe has been stationary for a while, even though you've pulled up out of the slips, you haven't actually moved the entire drill string at that point. You're just stretching the pipe when you pick up out of the slips. The first motion after the pipe has been stationary for a while, 99% of the time, is rotation. So when we kick in the rotary after a connection, the peak torque value that we see at surface, what we call static torque, gives us some insight into whether or not there are differential sticking effects starting to take hold on the string. And what you typically see is on the top of that chart there on the right is your static torque is just a little bit higher than your off bottom dynamic torque. And when you drill into a zone that's highly permeable, or you've got some sort of problem with your filter cake, if you're building up an excessively thick filter cake, you'll start to see the static torque separate from your dynamic torque. And that is an early warning that you've got to do something different or you're going to get differentially stuck. As soon as that static torque exceeds your drill pipe maximum torque capacity, you're stuck. We might not call it stuck. I've seen on certain operators, you never write stuck on your morning report. You'll say, we can't move the pipe. We temporarily can't move the pipe, or we're hung up, right? Stuck is a dirty word. But in essence, that's what's happened. So I really like watching my static torque. Doesn't tell me much about hole cleaning, doesn't really tell me anything about wellbore instability, but it's a great tool for preventing differential sticking. And I think Devi, at the end of our series, she's going to touch a lot more on some of the techniques we can use if you've got a model and you've got data in real time to try to get a better understanding of what's going on below the rotary table. So, David, if you want to go on to the next slide, that was what I was wanting to show. Thank you for doing that. Lots of different applications for torque and drag, right? For engineers, we tend to get really hyper fixated on the planning side of things, figuring out, do we need high torque drill pipe? Can we use the pipe that the rig's got? So drill string design, do we need taper pipe? Do we need heavier wall? Do we need higher grade? Great tool for drill string design, very useful in casing design, figuring out if our rig is big enough, maximum loads at the top drive and the derrick top drawwork's going to see. And I can't remember where this comes up in our agenda. I got to look. I think our very next presentation is going to be on casing and drill pipe wear and bending in the string. I haven't presented that here. We just don't have enough time to cover all of it, but that's part of planning, coming up with a trajectory that has low torque and or drag, working out whether or not it's possible to rotate during your cement job, working out the standoff, how many centralizers you need. That is very much a torque and drag problem. BHA tendency, figuring out if your BHA is going to have a rotary build or rotary drop tendency. That requires torque and drag analysis. Manipulating liner hangers and packers and gravel packers and all the completion hardware that we run in these modern wells. All that requires quite a bit of planning and a good torque and drag understanding. When we get into execution mode, all those models that we created now help us detect whether or not things are going to plan. You can't detect abnormal behavior unless you've modeled out what normal behavior should look like. So the whole condition monitoring that Devi's going to talk about will be a lot of techniques on how to understand that those things are headed your way. If you want to go to the next slide there, David. Lots of misconceptions out there. First one, when you're running in the hole, the pipe's in compression, and when you pull out of the hole, it's in tension. It is true that when you pull out of the hole, the pipe is in tension. That is not a misconception. What is a misconception is that tripping in necessarily means that you're in compression. In a horizontal well, it does, but in anything less than horizontal, it's not necessarily true that we're in compression or that the BHA is in compression. I've heard that said before, we don't have trouble tripping in the hole, but we do have trouble tripping out of the hole. It's because the BHA is in compression when you're tripping in. And we need to better analyze that before we just assume that's the case. Next one. Friction factor is the same for all operations. If it was a coefficient of friction, then yes, it should be the same whether we're running in, pulling out, rotating. but because it's not exactly coefficient of friction, it's very rarely the same. What we usually find is that pickup and slack off friction are pretty close, but your torsional friction tends to be a little bit lower than your pickup and slack off friction. And again, for the reasons that I mentioned before, things that we can't quantify in our coefficient of friction that get lumped into the friction factor, cuttings, beds, differential sticking effects, etc. Next one. When you're first doing modeling, a lot of times you'll ask somebody senior, hey, what's a good friction factor? Let's say 0.2 case hole, 0.3 open hole. That might be it, but it probably isn't. And that's why we like to do a range of friction. As low as 0.1, as high as 0.4, that will cover a pretty good range for both water base and oil base. Typically, you're going to be around 0.2 for 0.25 for oil base, and usually something north of that for water base. Next one. Yeah, I think I touched on this earlier, that the friction factor is known and controllable. It's not known, and it's not as controllable as we'd like to think. And again, that's why we have to do a range and not just a fixed value. Next one. This is a big topic, and I'm probably going to start a fight with Stefan here. Stiff string's more accurate than soft string. In a manner of speaking, yes, it is. However, if you go through the next click there, David, I would argue that it is similar to measuring the diameter of a walnut with a digital caliper versus a tape measure. So give me a couple more clicks. Is a digital caliper more accurate than a tape measure? Well, yes. But if you think about a walnut doesn't have one diameter, nor does it have a smooth surface. So when you measure it with your very accurate digital caliper, what part of the walnut are you actually touching at any given point in time? Whereas a tape measure, what the task of measuring the diameter of walnut, that's a crude measurement. And for a crude measurement, a tape measure is every bit as good as a digital caliper. And when I'm talking about stiff string versus soft string in a wellbore, we don't really know the true trajectory of the hole, and we don't know the diameter of the hole. We don't even know the shape of the hole. We might have an elliptical shaped hole due to wellbore instability and breakout. So to try to do very accurate stiff string modeling, you need to know the trajectory and you need to know the shape of the hole, and we almost never do. So from my perspective, rather than getting overly concerned about whether your model is stiff string or soft string, there are other more important factors to get concerned about. I think in the early days, there was a lot of talk about stiff string because it was a differentiator for some software companies that were trying to sell software. They said, we've got a stiff string model, it's better, you get better results. You really have to step back and say, what am I doing here? I'm making a brick or I'm making a walnut. I don't have that level of understanding that's required to truly do this higher end level of physics. Now, certain problems, I agree, you need to have a stiff string model. If you want to have a very good characterization of the shape of the pipe when it's buckled, if you know the size of the hole, stiff string is the way to go. If you want to understand BHA tendency and deflection, you got to have stiff string. If you really want to understand standoff, you got to have stiff string. But for the bulk of the use of the sort of problems we try to solve, a tape measure is every bit as good as a digital caliper. Okay, next slide. Probably the most common questions that I see engineers asked or that people ask me, especially today, and this is kind of in a US land context, if an operator's been drilling 1 mile laterals, they want to know, is it possible to drill 2 mile laterals? If they've been drilling a lot of 2 mile laterals, they want to know, is it possible to drill a 3 mile lateral? Once you've drilled your first 3 mile lateral, the natural question that everybody in management is going to ask is, hey, could we drill a 4 mile lateral? Well, torque and drag is a very useful tool for helping answer those sorts of questions. Probably second most common question is, once you start getting into those 2-3 mile territories, is, can we still use conventional motors or do we need an RSS? If we wanted to use conventional, do we need heavyweight? How much heavyweight? Where do we put the heavyweight? What about rocking? Will an agitator help? Do I need 2 agitators? Do I need 3 agitators? Those are the sorts of questions that pretty commonly come up now in the 2, 3, 4 mile lateral community. Getting casing to bottom, yes, that's a concern. Although because of flotation becoming more and more commonplace and high torque connections where people can rotate, we're not seeing as many problems getting casing to bottom as we did 10, 15, 20 years ago. Sometimes questions bigger rig. The question I hate the most, this is the worst question, is when somebody usually it's somebody with a C in front of their job title, the CEO or COO, they come and say, how far can we drill? Okay. How far is a rope? Give me some constraints. Are we talking about the rig we have, or can we build a custom rig? Can we get a different rig? Sky's the limit for drill pipe. How long do we have to plan? Can I order custom casing? Because extremely long wells have been drilled all over the world, the answer is probably as far as you want. Just give me enough time to get the stuff that I need. And that's what the torque and drag modeling allows you to do, is figure out what is it, the stuff that I need to make that possible. Next slide. Found this very descriptive meme on the internet, right? Elk City, Nevada is a bird sanctuary right in front of KFC. All of these examples of dumb things that we do with torque and drag modeling, these are dumb things that I've done. So I'm not pointing fingers at anybody other than myself, but we tend to get hyper focused on what we've done recently. As soon as management asks us to do something longer, then we just say, that's not possible. I haven't done that, so it must not be possible. And that's not a good answer. We need a torque and drag model to figure out if it's possible. Next one. Crazy looking well pass. Yeah, a couple of years ago when Shell had done the big horseshoe well in Permian Basin, there was SP papers and articles written about it, and everybody was amazed that they drilled this 2-mile horseshoe well, and there was absolutely nothing special about it from a torque and drag standpoint, particularly given the context of what's been done all over the world for the last 20 years with complicated wells. And so it's kind of more like what's common in your backyard. Just because it looks weird on paper doesn't mean that it's mechanically difficult. And that's where the modeling will lead you down that path. Just because it looks weird doesn't mean that you can't do it. Next one. I love this one. A lot of times we'll get a request, and it's because management asked the drilling department to do something that they weren't sure they could do. So they'll call me and say, hey, can you, get in our corner and show management that this isn't possible? How do you know it's not possible? Until you've done the engineering, you don't know if it's not possible. Usually the answer is it is possible if we do these 3 things. So don't try to use the torque and drag model to prove what you already know. Let it educate you on what's actually going on. One, I worked at a little company after ExxonMobil. The geologist was constantly wanting to change our target in the lateral. Like, oh, we got to go up, we got to go down, we got to go up, got to go down. I kept telling, oh man, if you keep making all these target changes, we're not going to be able to, our torque's going to be outrageous. Like, well, we bought you that fancy torque and drag software. Why don't you tell us how much torque's going to be when we get to TD if we do all these changes? So, I'm burning the midnight oil, running the calculations. Calculations say it doesn't matter. Well, that can't be right. I know that's not right. No, it is right. That's another problem that we have, is we get hyper focused on dog legs in the lateral. Dog legs in the lateral are highly overrated. They don't matter near as much as people think they do. Where the dog legs that matter are the ones way up hole. The shallow dog legs are the ones that you really should care about, especially on deep TVD wells. When you're over 10,000 foot TVD, dog legs, your nudge dog legs, are way more important than your lateral dog legs, particularly for torque. Torque is practically unaffected by lateral dog legs. Next couple of bullet points there, David. You could probably just go all the way to the bottom and I'll touch on them as necessary. Yeah. Oh, go back one. Yeah, there we go. RSS doesn't make all your torque and drag problems go away. And there's plenty of wells that, run out of torque or run out of drag, even though they drilled it with an RSS. I've touched on coefficient of friction and friction factor. Those are not the same number. Torque is a great one. A lot of times we just don't even pay attention to torque until we can't rotate. But I showed you that example earlier that the data that you collect from the top drive from a torque standpoint while you're drilling can tell you a lot of interesting stuff long before you can't rotate. So pay attention to it before you can't rotate. And I was talking to the NEWPARK guys, when they were graciously willing to sponsor this talk, one of the overriding themes of torque and drag is don't blame the mud every time something goes wrong. It might be the mud, but chances are that it's something else going on. Big dog legs up hole, or, we got too heavy a pipe, or, there's lots of things that can cause you to have torque and drag problems that are completely unrelated to the mud. Next slide. People ask me, what do you look for in software? I like good tools, right? Building that Jimmy, I have invested in some high quality Milwaukee hand tools. I like them because they work well. They're expensive. They work well. What does good software look like? In my view, good software is focused on the well, not focused on scenarios. Early torque and drag software was just set up for creating one scenario at a time. You looked at running this pipe in this hole, or you looked at running this casing in this hole. That's not what anybody's paying us to do. They're paying us to drill a well. So we should be looking at the entire well and all the operations that are required to construct it, not just doing one particular scenario. The other thing, easy to use. What does that really mean? Well, it's different things to different people, but there should be a big library of different commonly used components, different drill pipes, different motors, different collars, different casing. I shouldn't have to go manually type all that stuff in. It should be easy to copy and paste components. It should be easy to copy and paste scenarios. There should be default settings that are very close to what you would normally use. Don't just give me a bunch of blanks for all the inputs. If the software's smart, it's going to give me some sensible default settings. Everything should be sensitivity based because we live in a stochastic world, not in a deterministic world. All that means is I don't know exactly what some of those input parameters are going to be. So give me a sense of how important any particular parameter is. I also want to be able to see the loads at any point in the string at different depths in the well very quickly and easily. The calculation should happen almost instantaneously with a modern computer. All graphical output, a chart with a bunch of numbers in it means nothing to me. I want to see graphs. And, as we're starting to learn more and more about this, the hydraulics needs to be coupled to torque and drag. Hydraulics very much impacts the loads that we see. So those two things should be run together, tied together, not separate. So if your software does these things, then I'd say you've got some good software. Now, on the flip side, if you've ever, next slide there, David, if you've ever had a little problem that you needed to solve in your garage and you didn't want to spend a bunch of money on Milwaukee tools, so you went to Harbor Freight, certain things you buy at Harbor Freight are great. If it's a one use job, I bought a heat gun from Harbor Freight because I just had one little thing that I needed it for. It was $15. Yeah. But if you're making your living off of those tools, or you're going to use it a lot, Harbor Freight is not where you want to go. I've got a Harbor Freight ratchet and the thing's falling apart. And I cut my hands every time I use it because the little snap ring that holds it together, it's, broken off, and I need to just throw it away. What does bad software look like? Well, it's a big monolith, perhaps, that was built by committee. One thing we know about the government is it does not work efficiently. And if your software was built by an entity the size of the government, it's not going to work efficiently either, because you're going to have lots of competing parties that are all trying to put their little special sauce into this thing. Big monolithic systems that were built by a huge group of people usually do not work very smoothly. Software that was built by developers and data scientists rather than the people that actually use it tend to not work very well. So that's a question I would ask is, did the users drive how this thing functions? I'm not saying that users need to be writing the code. We absolutely need software developers and data scientists to make good software, but the structure and layout of how it works, how you're solving problems with it every day, needs to be defined by the user, not by the people that write the code. Another one I love is the cloud. Oh my God, we're so obsessed with the cloud these days. Whatever piece of garbage software you've made, as long as it's on the cloud, it must be amazing. I could care less if it's on the cloud, right? That is not what's important. It needs to function, do the calculations, do them quickly, whether it's on the cloud or not. If it happens to be on the cloud, that's great, but the cloud itself doesn't make it good. If I've got redundant inputs, if I have to put in the same stuff to do a torque and drag calculation as I do a hydraulics calculation, that's nonsense. I shouldn't have to do that. If I can't copy and paste, if there's tons of crazy esoteric, variables and inputs that nobody understands, I'm not trying not to name names here, but there's a famous casing design software that that has all these, thermal coefficients that nobody understands what they mean. And even the experts that do understand what they mean, none of them agree on the proper values. So if your software has that, that's not good. My all-time favorite, if your software has a calculate button, it is Harbor Freight quality, right? Calculate belongs in the 90s. That was back when we had hardware that you needed a calculate button. There was 15 minutes in the 90s where Vanilla Ice was cool. There was also 15 minutes in the 90s where the calculate button was cool. Your Torque and Drag software should not have a calculate button. My iPhone does not have a calculate button. It does it automatically. That's the way the software should work. Next slide. Did I lose you, Dave? There we go. What I mean by the hardware. So when the Torque and Drag software first evolved in the late 80s, early 90s, if you look at the Moore's law chart of how every year the number of transistors in the processor doubles, we were sitting at a level there where a 386 or a 486 Pentium was like unbelievable computing horsepower, right? In the early days of Torque and Drag, we have got 3 or 4 orders of magnitude more CPU power than we did back when the code was originally written. More importantly, we've got several orders of magnitude more RAM capacity. And something I was not aware of, some very brilliant software developers brought this to my attention years ago, is that the slowest possible thing your computer does is write to the hard drive. Well, back in the 80s and 90s, any calculations that were done had to be written to the hard drive because we had hardly any RAM, right? I think our first computer was a 386DX and it had like 400 kilobytes of RAM. That's hardly anything by today's standards. I haven't bought a laptop in the last decade with less than 8 gigs of RAM. 8 gigs of RAM. So all the calculations that you do can happen in RAM. Writing to RAM happens almost instantaneously. There's very little slowdown between the CPU and the RAM, certainly compared to writing to the hard drive. Your software should not be writing output to the hard drive. That slows everything down ridiculously slow. The sort of math that we're doing should happen instantaneously if the software is structured correctly. Now, what I've found is the companies that first built Torque and Drag software in the 80s and 90s, by the time they got to the point where all this amazing hardware was available to them, it was such a daunting task to go back and restructure the software to work differently that they just didn't. So they kept on adding and adding and adding to the code. But really, you got to burn the whole thing down now in the 2023. Start over with the sort of hardware that you've got available to you now to make it work efficiently. And for the companies that have been out there for a long time, it's probably time to burn it down to the ground, rewrite it in an efficient manner. Next slide. So a few New Year's resolutions. DEs, I hope you participate in the series and become very comfortable and competent running software. I hope your management buys you good software and not the Harbor Freight software. Saving money on software is not the place to save money. For those of you companies out, and there's a lot of them, there's a lot of software companies out there, don't stop investing. There's one major company in particular that stopped investing in their software for a period of time. I think they're putting money back into it now, but as soon as you stop, somebody else is going to pass you. Keep trying to make it better, faster, and easier to use. The users are the ones that you need to be listening to. The people who use it every day should craft the way your software works. AI companies, this is a slight irritation. What you're doing right now with Torque and Drag is not all that useful. Let's make 2023 the year to make your Torque and Drag useful. If you can't do planning, if you can't manipulate the inputs, if I can't unlock the case-toll friction factor, if I can't do casing flotation, if I can't do fill-up points, if I can't put centralizers and swivels and all these other very important Torque and Drag effects in, then it's really not that useful. There's some AI companies that don't even use a physics model. I went and met with them a couple of years ago. Like, yeah, we do Torque and Drag. I'm like, okay, well, which model do you use? Like, oh, well, we use our big data analytics to predict what your pickup and slack off will be based on, what you did previously. Like, that's called drugs. You're doing drugs when you calculate Torque and Drag that way because you're basing everything on what you've already done. You can't predict something that dramatically changes if it's different from what you've already done. If I drill a significantly longer lateral, if I change my drill pipe, if I change my well path, those things the predictive analytics can't anticipate. Data without a model isn't science. Last slide. So the future, what I really hope to see is more and more software packages will tie hydraulics. And we haven't really touched on this. This could be a whole nother idea for you, David, 7-part series on geomechanics, but tie hydraulics and geomechanics into torque and drag without making it overly complicated. I hope we see more and more of that in the future. And here's a freebie for NOV. If anybody from NOV is on, I'm quite pleased with myself on this. If you could tie torque and drag and hydraulics into rig instrumentation so that the driller, the guy who's running the rig or gal that's running the rig, can see where are my maximum and minimum limitations on the gauges. Why is it still a Martin Decker and not a Smartin Decker? A Smartin Decker, in my mind, would be a digital weight indicator that's got lines that are constantly being computed by a torque and drag engine to tell you what's the maximum you can pull, what's the minimum you can slack off on your torque gauge, what's the limit before I break something in the strength. We need that sort of stuff. And it really would not be that hard to tie torque and drag and hydraulics into our rig instrumentation. I'm not talking about the AI companies that are pseudo doing that. I'm talking about the companies that put the gauges on the rig floor that the driller actually uses to run the rig. That's where the integration needs to happen. And to continue on that kind of train of thought, where we also really need it is on the cement unit. The cement unit needs real-time torque and drag and hydraulics so that we can make better decisions when we're placing our cement. If you haven't overhauled your software in the last 15, 20 years, you really should. When we were rebuilding that 1980 Jimmy, it was real tempting to take this 1980 small black Chevy motor, had 100,000 miles on it, so we knew we needed to rebuild it. But as long as you're rebuilding it, why not do something cool, right? Do an LS swap, put 2 turbos on there, do something that actually moves the needle in terms of performance. Just rehashing old code doesn't really move the needle. We need a step change here, and there's a lot of opportunity because of the hardware that we have available to us today with computers to do that. I haven't put it on this slide, but another thing, if you're interested in this sort of stuff, Paul Patusik at ExxonMobil's started a initiative to do open source software where various entities contribute code, and it's managed by a committee, and everybody has access to it. And rather than reinventing the wheel, collectively as a group, we can add into that and make this shared code, kind of like Linux back in the day, better and better and better over time. Now that, doesn't work with some companies' business models, granted, but, I think for a lot of companies, that's an interesting and compelling idea. So that's something to look into. But for me, the future is just trying to get the calculations in front of the person who needs it most, and that's the guy running the rig. Okay. I've yacked on here for an hour. I probably don't need to keep doing that, David. So, questions?
Brandon, thank you so much, sir. I'll go ahead and pull this off the screen, and then if we need to, pull it back up. So we do have plenty of questions. All right, guys, if y'all have got any questions, be sure to throw them out there. And then there we go. Brandon, you are the GOAT.
That's from anonymous. That's probably my wife, if I had to guess.
One of the kids, right? Somebody else said, great presentation. John DeWart said that for the last comment there.
There it is.
Sourcedrilling.org. And then Peter Harvey says, thanks, Brandon. Thanks, David. No worries. All right. So let's jump over to the questions. So anybody if you guys have got any questions about any point in time during the presentation, I've already started a whole bunch of them. And we'll start going through those. So we'll try to be able to remember exactly what part this goes back to, but should be able to, through the question, be able to reference back. So this one just says contact area ? I think this goes back to determining friction.
Yeah. So contact area. If I had 5-inch drill pipe, and this is just like theoretically, if I had 5-inch drill pipe or 7-inch casing that weighed the same, and they don't weigh exactly the same, but close enough. Let's say 7-inch, 23-pound casing and 5-inch drill pipe. 7-inch casing has more contact area than the 5-inch drill pipe does. But because they weigh the same, if what we're just talking about is sliding friction, it takes exactly the same amount of force to push the 7-inch casing in the hole as it does the 5-inch drill pipe. Now, That's just pure sliding friction because we've got those other factors that I talked about, plowing cuttings beds, differential sticking effects, any wellbore instability that's going on, hidden tortuosity. The 7-inch casing, because it's stiffer, is going to be more sensitive to hidden tortuosity than the 5-inch drill pipe is. What you tend to find, whether you're using a soft string model or a stiff string model, is that running 7-inch casing attracts a higher friction factor than the 5-inch drill pipe did. But the basic physics says that the contact area doesn't matter.
All right. And so then Mason, I think that's what it is friction or friction factor. I think that kind of coincides with the previous question.
There's like 3 things, right? There's friction force, how many pounds, or, if you like communist units, kilodecanewtons. How many pounds of force does it take to move an object? That's friction force. Coefficient of friction is that laboratory measurement of 2 surfaces sliding across each other. And then friction factor is what we infer the coefficient of friction to be when we overlay actual hook loads or actual torque onto a theoretical model. So three different things, and you kind of have to compartmentalize them in your mind.
All right. Then Dr. C says speed does not change the amount of friction, only under dry friction.
Right. If you're not taking into account fluid effects. As soon as you take into account fluid effects, which you should, which I'm advocating for, your hydraulics engine should be tied in to the torque and drag program. Speed absolutely matters.
There we go. So this one's from Shreve. What is the difference between buckling and bending?
Yeah. Bending is just pipe that's not straight. When we've got pipe that goes around a curve, there's additional side forces that are present because it takes energy to bend that piece of pipe. Bent pipe is not necessarily buckled. If you think about a horizontal well that goes straight down and around out into the lateral, actually the hardest place in that well to buckle pipe is in the curve itself. Bent pipe is the hardest pipe to buckle. The easiest pipe to buckle is straight pipe in the vertical part of the hole. If you put straight pipe in the vertical hole and just a little bit of compression, it starts to wiggle. Out in the lateral, that's the second easiest place to buckle the pipe. It's a lot harder to buckle pipe in the lateral than it is to buckle pipe in the vertical. But in the lateral, you reach a point where you've put so much compression on the pipe when you're pushing on it that it starts to wiggle back and forth, just like your hose. Your hose video was perfect, David. I'm telling you, it was the perfect lead into all of this. But when the pipe starts to wiggle back and forth, you're starting to create additional side forces due to the pipe not being straight anymore, pushing into the side of the well. Now, eventually, you reach such severe buckling that the hose, if you were in a tubular pipe, it will coil up. And at that point, you can't move it any further. You've reached lockup. So if you talk to the coil tubing guys, lockup is the depth of the well where you just can't go anymore. You can have that with drill pipe too. We can have that with casing. A lot of 5.5-inch casing that we run in 8 3/4, 8.5-inch hole doesn't go to bottom because of helical buckling and lockup.
There we go. But no, I had no idea I would be so spot on with the water hose.
Nailed it.
All right. Here's one from Divine. How can I use the torque and drag model while tripping in or out of the hole during drilling, rotary or sliding mode, or rotating off bottom to calibrate coefficient of friction in these cases and open hole?
Yeah,
there's a lot in there.
That's a bigger question than you probably even realize. Or maybe you do. I don't know. He's just feeding me a really great question. The notion of separating cased hole friction from open hole friction while you're drilling is nonsense. You cannot sense what the cased hole friction is 1 foot after you've drilled out the float sheet. And what I mean by that is when the only thing you have is drill pipe inside cased hole, you pick up the pipe, you slack off the pipe, you take the measurement, you compare it to the model, you know what your cased hole friction is. But as soon as you drill out, now you've changed the material that the pipe is sliding against. You've got cuttings out in the open hole that have moved up into the cased hole, and now you're starting to change that surface. So just because you made a measurement back when you were in cased hole doesn't mean that it's going to stay that level as you go to drill your lateral. So what I advocate people to do is do not lock down the case toe friction factor. It should be an average number from surface to TD while you're drilling the lateral. And you really have no way of trying to have a discrete value in case toe versus open hole, unless you were to have some sort of measurement sub in the string that was telling you what your tension and torque is back in case hole at all times. But what you'll see in those cases when we've done that is that the case toe friction changes as you drill. Now, running casing is a more static environment. So as you're running casing, you can get a sense for what your case toe friction factor is, and you can lock that down and say, okay, I know it's 0.2, and then do a sensitivity analysis in open hole. But while drilling ahead, there really is no easy way to know what your case toe friction is. So you just run an average across the entire hole, which, by the way, if you read Rap Dawson's original SP paper, that's exactly what they were doing. They didn't break out the case toe and open hole, but then we thought we were way too clever, and all the software companies made it so that the case toe friction was locked down. Don't do that.
Lessons learned. All right, another question from me. How can I estimate maximum torque on my drill string so as to enable me to select the optimum drill pipe size and connection?
Run, torque, and drag.
Boom.
Bigger answer is if you've drilled wells
watch
in
the
an
torque
area.
and drag series. That's
yeah, exactly. But the bigger answer is, look at your offset wells to see what the typical friction factors are so that you're forecasting with an appropriate friction factor range. If you're going to modify things significantly from what you've done in the past, if it's different hole sizes, different mud types, then, your previous history is not all that relevant.
Okay, so this one's got a whole bunch of lead up, but the question is, what is the reason to not run individual friction factors?
Usually it's different. No, those numbers are garbage. They change radically. They depend on the region. They depend on the rock. They depend on the mud. Don't do it. I've been doing this for 20 years, and that's probably one of my strongest recommendations is no matter how much you think you know what the case toe friction is, you don't. It's not a number, and it changes.
There we go. Maybe we need to do some more demonstrations with the water hose. Through the key issues is hole cleaning and differential sticking. Purely geometrical torque and drag is rarely what causes train wrecks. Pickup slack off weight charts are principally there to disagree with that. I think there was a question leading up to that, but maybe I started the wrong one. That didn't make a lot of sense.
No, pickup and slack off. Yeah, pickup and slack off charts are not in real time mode. Are not primarily there for geometrical torque and drag. They do illustrate geometrical torque and drag, but they absolutely help you detect hole cleaning and differential sticking problems. So, yeah, we should run them in real time to anticipate and react to hole cleaning and differential sticking problems. Here's what I'll tell you about U.S. land is very rarely are we getting into hole cleaning problems. We're drilling small hole that's easy to clean. That's why it's really not that big of a deal. We don't need to do pick up and slack off at every connection on U.S. land small hole. If I was drilling 12 and a quarter at 85 degrees to 30,000 feet on an ERD well, absolutely we need to be watching torque and drag because hole cleaning is a very big concern. Anywhere where you're drilling through permeable formations, differential sticking is a risk. So that's why that static torque measurement is so important.
All right. So jump into, is there a software that uses surface measurements to infer downhole friction like bit torque or calculate top to bottom, the reverse of most software?
Yes.
Okay.
That's what the overriding feedback that we got when we're talking about this series, you don't want a sales pitch. I don't sell software, and I'm not going to pitch somebody else's software. I'll let them do that. But there is torque and drag software out there that will infer what your bit torque is through using the torque and drag engine. And that is one of the ways that we calculate downhole MSE, particularly if you don't have a motor. That example that I just gave you from Mississippi, we're drilling those horizontal wells with a rotary steerable that is not run with a motor, back the way God intended before we started coupling motors with rotary steerable tools. Without a motor, you don't have a way to infer directly bit torque like you do with a motor. So with a motor, we use the differential pressure and torque relationship to figure out what the bit torque is. But if you don't have a motor, you have a torque and drag engine to calculate how much of your surface torque is actually coming from the bit.
Okay, Divine coming out with some more questions here. How can I use torque and drag model buckling analysis to validate my well profile and drill string design and prevent loss of divine,
Loss of divine
by eliminating drill string failure?
Yeah. Watch this series.
Boom.
Yeah.
Okay, there we go. There's a lot. This is just the introduction, you guys. This is
just getting warmed up.
We're just getting started.
That's right.
Just getting started. We said there were going to be 7 episodes. There's going to be 7 more episodes after this one because Brandon's going to come back
with far more interesting and qualified people talking to you. So get excited about seeing what they have to say.
Yeah, and that's definitely not me. Okay. All right, here we go. Anyone in the series going to talk about true and effective tension?
We should. I can't remember if we've got that on the.
I was going to say you're better qualified to answer this than I am.
I don't know if we put that on the agenda. We'll see if we can't get somebody to cover it. If they don't, I'll talk about it in our wrap-up series.
There we go. I know we kind of covered this one, but it was still a question. What is stiff and soft string?
Yeah. Simply put, soft string assumes that the drill pipe follows your well path like a wet noodle, that it uniformly contacts the hole. Now we know in reality that the drill pipe or casing, whatever running in the hole, has some rigidity. So if you imagine like a dip in the well path, that the pipe is going to actually span across that dip, depending on how stiff it is. It's not going to follow the path perfectly. And that's what the stiff string model aims to do, is characterize the shape of the string rather than letting the well path dictate the shape of the string. And as I said before, the difficulty with that is you need to know the true shape of the hole. You need to know the true trajectory of the hole. And one other thing that we don't really know is the true geometry of the drill string. We assume that all the tool joints are the same diameter. We assume that all the pipe is straight. It's not. None of those things are true. So it's like doing finite element analysis on an object and you don't know what the shape of the object is.
I like that. How long is rope? Exactly. From vertical well, the soft string will reflect better torque drag model.
Yeah, which one's better in a vertical well? Well, I think that the pissing contest between stiff string and soft string is really unnecessary. Either one will produce equally good results. What's more important is how you use the inputs. Case in point, when we were working at Mobile had a stiff string model, Exxon had a soft string model. Exxon was drilling all these ERD wells offshore California. They'd run it through the soft string model, and then just for verification, I'd run it through the stiff string model. And the results were almost exactly the same, like within 2% of one another.
All right, stop screen share. That's what was making that jump around. All right, there we go. Dog legs in the lateral matter to completions, though, correct?
Maybe, maybe not. It depends what you mean by completions. If we're running a bunch of open hole packers or frac sleeves that are very large diameter relative to the hole, they're big diameter and they're long, yeah, dog legs start to matter. But if what you're talking about is doing coiled tubing intervention for a clean out or stick pipe clean outs, dog legs in the lateral don't really matter that much, just like they didn't matter for the drill pipe.
I know you're not going to answer this next one, but I'm still going to put it up here. What's considered Harbor Freight software?
I've given you the characteristics of Harbor Freight software, so you'll just have to do that homework on your own.
Software sold at Harbor Freight.
Well, yeah, and if you don't live in the U.S., then the Harbor Freight analogy is maybe not great. But yeah, if there's a calculate button, that's a big red flag for me.
A lot of people are going to be changing calculate to
just get rid of if you have a calculate button, hide it.
The John DeWart says human graphic interface on the rig floor is needed upgrade. Agreed.
Who likes the Smart and Decker trademark?
That's That's a very
I'm not a
smart
marketing
idea.
guy, but I think the Smart and Decker is an obvious win for NOV.
Somebody needs to tag David Reed to watch this. So somebody
Yep.
tag him in the comments section, so he'll jump on that one. All right. So then we've had a ton of comments since we started taking questions. All right. But also need to get right inputs to generate the limits. How long has it taken to get rig crew to get the right info into soft torque system? Our
Yep.
buddy Ian.
Ian knows full well. Yeah, soft torque's a good tool, but it works like garbage if you don't have the inputs in there correct.
Yeah. And then we started getting, great presentation. Thanks. Very insightful. Brandon, thanks a lot. Great stuff. Thanks. What is the next series 207? So next week is with Oleosoft, and they are doing
Side forces, bending, stress, fatigue, stretch and twist, casing and drill pipe standoff, kind of a lot of the ancillary effects of torque and drag that are easy to ignore, but when you really sit down and think about all the implications that they have, you can do a lot of good if you look at these things and understand them. So that should be a great talk.
I'm glad that you're prepared and have the lineup in front of you. I need to do that for next week, Tracy. Have the lineup ready to go. Print it off for me. All right. Daniel says, great presentation. Besides, great informative presentation, Brandon. Donna says, great presenter and great presentation. Very interesting and informative from Dean. I can't stop listening and learning throughout the whole session from Ari. Thank you so much. He works at NOV. I think he's at
There you
NOV.
go. All right.
He's gonna.
All I need is a $1 royalty per Smart and Decker unit sold
per day.
Per day.
Yep. Then Asif says, great presentation. Adrian, thank you. Very informative. Nice work. From Warren, great presentation, says John DeWart. Mentioned that torque is not an indication of hole cleaning. Can you expand on this?
Yeah, this is another one of those, like, after 20 years, you're like, it doesn't tell us what we thought it told us. Torque is almost never a leading indicator of cuttings bed buildup. Pickup and slack off is almost always, I say almost just because, I mean, nothing is absolute, but I've seen very few examples of where torque told you that you had a cuttings bed buildup before pickup and slack off did. And if you think about your cuttings bed building up, when you pick up and slack off, the tool joints are plowing through the bed. So they're interacting and sensing that cuttings bed thickness much more than just rotating drill pipe in the bed. That's providing very little resistance for the drill string to rotate, much less so than picking up and slacking off. So by the time you can't rotate because you've got a cuttings bed problem, you were ignoring pickup and slack off for a long time. That's why I say it's not a good indicator. Your best leading indicator is pickup slack off.
Yeah, that's was it driving through the review mirror?
Yeah.
All right. Carlos says, great presentation. How significant is the effect of sheave friction on hook load calculation?
God, we need to add that to the agenda as well. It is important.
Looks like we're giving your to-do list on the second time
right.
you come on.
Sheave friction is an interesting one. It is important, but you can compensate for it by actually just measuring sheave friction. And what I mean by that is, with nothing suspended by the top drive or the hook, run the blocks up and down and look on the weight indicator how the blocks appear to weigh something different depending on whether you're moving up or down. And there's a great SP paper on, I'll post it on LinkedIn, where you can see the description of how the physics works out. But in essence, your blocks appear to weigh more when you're running in the hole, and they appear to weigh less when you're pulling out of the hole due to sheave friction. And you can either put in the sheave friction in some software, or in other software, you have 3 different block weights. Now, the blocks don't actually weigh something different, but they appear to weigh different up, down, and stationary, and that's how you compensate for that. Some wells it matters. In other wells, the differences are so small that it's not really worth worrying about too much.
I weigh different morning, noon, and night. There we go. Just as a quick update, the presentation, we will share the PowerPoint presentation, not probably on Thursday. We'll post that online on Thursday. So anybody that wants to be able to see the PowerPoint presentation, we will add that in there Thursday. Also, just because we're taking a quick break here, be sure to link up and follow Brandon on LinkedIn. Get in touch with him. If you are a drilling engineer, you work at a company, and you need some help, he does do this for a living. So he took the time to be able to give a free presentation. The least you could do is, if you run into problems, is to hire him to help you out there. If you want to follow me on LinkedIn, and there's also a little notification bell. I know it seems like social media cringe for me to say this, but if you want to get the notification of when we go live for doing any of these, including the Vidor Locksmith Show, which we will be live Friday on, be sure to click the little notification icon. Then you'll get an actual notification as soon as we go live. That's it for now. Then back to this LinkedIn question. Question, please, one more time. Can you explain the difference between friction factor and coefficient of friction?
Yeah. Coefficient of friction is something that we can measure in the laboratory. It's called a lubricity tester. All the mud companies have one or have access to one. And they'll take, just to simplify things, a plate. They'll put some mud or lubricant on the plate. They'll put a device that puts a load on a steel rod on that plate. They'll rotate the rod and infer what your coefficient of friction is from rotating the rod on the plate with the lubricated surface, so that they can assess the efficacy of different lubricants or different mud systems. You can see how that is very different from what we do when we drill a well, where we've got drill pipe with tool joints and cuttings and casing and a rugose hole that we don't actually know the shape of. And what we do is we measure the torque at surface across this entire long, 2, 3, 4, 5, 6, 7, 8, 9 mile well. And then we compare what we measure at surface to what we calculate from a torque and drag program. Friction factor is back calculated friction using torque and drag software and surface measurements at the rig. Very different than the controlled environment in a laboratory where you're measuring coefficient of friction. We use the two terms interchangeably. We really shouldn't, because they are different things. The friction factor is influenced, and some people call it a fudge factor. Call it that if you want, but it is influenced and lumps in a bunch of little effects that you can't break out into discrete pieces like you could in a laboratory setting.
There we go. All right. Great presentation, Brandon. Thank you for hosting, David. You're welcome. This Duncan's asking the question we already answered, so we'll jump past that one. Friction factor is measured as the rotation between a known coefficient of friction and a real one.
That's not the way we use it in torque and drag software.
But if use stiff string model, it gives results with increased torque and axial stress. If the string qualify with this model, it is good. However, we go with the soft. What will you suggest? And I just want to say thank you for everybody that asked questions. Even if English is not your primary language, it may not sound great, but we understand that you're probably using Google Translate or just doing the best you can. And we appreciate it. Please do not hesitate to ask questions.
Yeah, so I think the question is, if you do your calculations and stiff string says that you've got higher load, but the soft string says that you've got a lower load. And actually, sometimes you see the opposite. Is soft string is more pessimistic than stiff string. It depends on the circumstances. I think Stefan will get into that. But if you were running two side by side, use the more conservative one. I'm a conservative guy. I don't want to break anything. So if there's a question, go with the one that's more pessimistic.
There we go. And I'm just saying this, there's tons of comments coming in. All right, great president. How do you think geomechanics could be used as an improvement to torque and drag models? Excellent question, Andres.
How long is a rope? One example. So right now in the Delaware Basin in Permian, we do this every single day. I've got a couple clients where, the wolf camp, particularly wolf camp A, is particularly unstable. It's, you need a certain amount of mud weight to keep it stable. So we try to run a geomechanics model in parallel to doing torque and drag and hydraulics modeling. And when we trip, we've got a great opportunity to validate the geomechanics using real-time drag data. When you see, so you've calculated where you think breakout's going to happen, and then you compare that to what your hook loads are on your trip out. And when you've got a mirror image of where you've got overpull and where you've predicted breakout, your geomechanics model is probably pretty good. Now, if your geomechanics model says that you should have horrendous breakout, but when you go to trip out, everything's perfect, then there's probably a problem with the geomechanics model. So you're using it for two reasons: to try to, in real time, adjust your mud weight to prevent wellbore instability problems. But when you do get into wellbore instability, that valuable drag data feeds back into the geomechanics model to make it more accurate for future predictions. I think we need to do more of that as an industry.
Sometimes we noticed our pickup weights are coming lesser than slack weights, especially in surface holes, also with vortex BHAs. Any ideas?
Probably has nothing to do with vortex. Probably has everything to do with sheave friction. So particularly when you're shallow in the hole, where hook loads are not that high and there's very little drag in the hole, when you start seeing that, it's because of block weight differences or apparent block weight differences due to sheave friction. So Asim, I hope I'm getting your pronunciation correct. Have the driller check what the block weight appears to be without anything connected to the top drive. Move them up and down and see if you actually see that inverse relationship where your slack off block weight is higher than your pickup block weight. And you can feed that into you could even manually trick your software by just setting up a couple different scenarios with a different block weight for picking up and different block weight for slacking off.
All right, next one. This one's from Jake. Given the same inputs, how much difference between final calculations of soft and stiff string models?
Everybody hates the depends answer, but what I will tell you, for most of our geometries, so 5-inch drill pipe and an 8.5-inch hole, 5.5, even 5.5, even 5 7/8 drill pipe and an 8.5-inch hole, 4-inch or 4.5 drill pipe and a 6 3/4 hole, 9 5/8 casing in a 12 1/4 hole. Those sorts of clearances, you're going to see 1 or 2% difference, unless there's just horrendous dog legs. And by horrendous, over 15 degrees per 100 usually. And sometimes even if you're 15, 20 degrees per 100, if it's just, an errant dog leg here or there, it's very little difference. I was quite surprised, back to that example from ExxonMobil, when they were running these super long 9 5/8 strings out in California at SLIU, we were really, they had, I think, a 6-degree dogleg in there. Like, oh my God, we're not going to get this casing to bottom. We better run it through the stiff string model. Stiff string model says, no, it doesn't matter. What? That can't be right. So then we ran a scenario and went, well, okay, what if we ran 20-inch casing through a 20-degree dogleg? No, that doesn't matter. What? That can't be right.
There we go. All right. So I want to jump down to this one real quick. When is episode 2? So every episode is going to be on Tuesday at 8 a.m. starting today, right? We started it today, 8 a.m., let's say Houston time, right? Everybody can usually calculate to Houston time fairly well. 8 a.m. Houston time, all the way up until the end of February. So we're going to have 7 more episodes after today. So there was actually a total of 8 episodes because Brandon's coming back to do another one. And once again, because we need to do this, special thanks to NEWPARK for sponsoring this and helping us put this together. All right, guys, the number of questions is absolutely blowing me away here. So if we miss one, I apologize, but I mean, we can't keep Brandon here all day, right? How important is it from your point of view, to monitor or not your drilling fluid's lubricity via lubricity tester?
Well, I haven't spent a lot of time worrying about it that much. I would say early in my career, I tried to, and then it just felt like a fool's errand after a while. Now, somebody may present some, a case history or data or facts or something that would change my mind. So I'm certainly open to being wrong about that, but it's not something I worry about that much. I don't really care what lab quoted lubricity is. I'm far more interested in what field performance looks like. That example from Mississippi, is one. where you've got the tools at your disposal to figure out what the performance of a given lubricant is going to do in your field. Last night I was texting with one of our company men. Last night we were talking about, should we throw some beads in here when we're back reaming out of the hole? Well, we didn't really see much benefit from it on the last wells when we monitored torque and drag. So let's not just throw money down hole because it feels like the right thing to do. We've got the data that says it doesn't really matter. But when the bead guys come to your office, it's very impressive. They throw beads on the conference table and slide a book across the table, and it just keeps sailing like you're on a shuffleboard table. But that's not the environment that we've got downhole. So I don't really care what the velocity tester says.
Just because I saw this question, I think this one would be very interesting to answer. Can you share some case histories where torque and drag limits were severely exceeded?
Yeah, we'll add that to our to-do list for episode 8.
Oh, yeah, there we go. Regarding this, and then I guess we'll add this one to episode 8 as well. You appreciate if you could share the paper regarding the sheave friction explanation.
Yeah, you keep peppering questions. I'll see if I can't find the number, but if I can't find it, I'll post it on LinkedIn afterwards. But I think I've got it here handy.
And I'm late again. Are models currently simulating air drilling?
You can, and I have. The one time that I did it, people aren't doing that much air drilling. But when I had the friction was very high. It was very, very high, like 0.6 or 0.7, I want to say. Straight air, no mist, no foam. It's West Texas. Not that matters, but yeah, it was high.
We did air on our water hose.
Yeah,
there's no water even going.
That was air drilling. Yeah,
that was air drilling or air tripping. We weren't even drilling. Somebody pointed out that we didn't even have a bit at the end, so we were just running water hose casing. Miguel says, "Great presentation." Just a comment: make sure that your pipe is well weight calibrated. We have seen like a 15% of weight higher than specs info. So I recommend to get the calibrated weight to run any torque and drag model.
100%. And I would guess that my good friend Neil Armstrong is going to talk about that in his presentation. You can measure the weight at surface, or there's ways through monitoring that you can infer what your actual pipe weight is. That rotating hook load line is kind of your calibration or pipe weight verification line. And I'm almost certain that Neil will talk about that. If he does, Neil, if you're watching, cover that.
There we go. Note to Neil. Somebody tag Neil in the comments if they would, please. So this one's from Henry. How do you compensate in a model the friction while stripping through an RCD or MPD system?
Yeah. So there's two pieces there. The MPD pressure itself lifts the string. So the way I do it is we include what our surface pressure is, and that corrects your hook loads for that back pressure. And then there's also, most software has an adjustment box if you've got discrete drag through the RCD itself. So the rubber itself closing in on the pipe. If there's an extra 1,000 pounds or 2,000 pounds or whatever the force is, you can manually add that.
So there's a great comment. Awesome job as usual. Thanks, David Gibson and Brandon Foster. Stay away from the drugs and keep on doing science.
That's right. It's like the DARE program. Stay off the drugs.
Felipe says, I am sorry for those who missed today's episode. I am
too kind.
Guy from next door says, good stuff from next door. There we go. Let me see. Make sure. Here's another one. Kaleem says, for torque, increase of RPM will increase friction coefficient led to increased torque. What does actually contribute the phenomenon?
Yeah, that's so. I should have touched on this. So if you go by the laws of friction, your torque is completely independent of RPM. If you've got 20,000 foot-pounds at 10 RPM, you should have 20,000 foot-pounds at 80 RPM. But oftentimes, if you do that test on the rig, you see that they're not the same. So there's two things that primarily drive that. One is vibration of the string. So you can use an off-bottom RPM test to infer lateral vibration in the string, which is, there's actually been some papers that have talked about that.
Ooh.
It's a worthwhile exercise to go through. Two is the fluid friction that we talked about. And under most geometries and circumstances, that's a pretty minor effect. So that's not a huge one. And the last one that we just found again in Mississippi is we had a little bit of junk in the hole from drilling out a DV tool that we didn't get out. And we found that we were hypersensitive to RPM until we finally got that junk ground up. So it's kind of interesting. But you shouldn't see very much difference if you don't have lateral vibration, if you don't have junk, and you don't have a ton of fluid friction.
Okay, I'm hoping that I did not skip past too many questions because I know I started moving around. Did we do this one? Best guidelines for taking pickup and slack off data points to calibrate torque and drag model with pumps and RPMs, or better without?
Henry, you're opening a can of worms. So back in the day, what we used to tell people is only do pickup and slack off with your pumps off with no rotation. And the thought was, well, we don't want fluid friction to be influencing the results. Then we kind of had an epiphany that was causing a lot of wellbore instability problems, because we were drilling wells where the mud weight was just barely higher than the breakout gradient. And on really long ERD wells, particularly in small hole sizes, you have a horrendous swab effect. Sometimes 1.5, 2 pounds per gallon below mud weight. And when you go and intentionally, every single stand, do a pickup weight with the pumps off, you're swabbing the hell out of the hole. So we were creating our own wellbore instability problems by virtue of this pickup and slack off routine that we were advocating. Now, what I would tell you, the benefit of hindsight, is you really should not be picking up the pipe without the pump on the hole if you're in one of these wellbore instability, concern areas. So always do your pickup and slack off with the pump on. As long as it's done at the same rate, you do it the same way, then it makes it much easier to interpret. I would encourage you not to rotate, because it is an extra level of complication to compensate for the effects of rotation. You can do it, but it's just easier if you don't rotate. Now, what you'll find on really long horizontal wells or really long ERD wells is that you eventually reach a point where you can't move down without rotation. So at that point, you just stop taking slack off readings and you just focus on pickup weights.
All right. We'll throw out maybe one or two more questions. How reliable is top-down analysis? Because as you said, friction factor is not known and it changes over time.
Yeah, how reliable? It depends on what you're trying to use it for. So if what you're trying to do is infer bit torque to get a sense for drilling response or downhole MSE, it's good enough. If on every stand you're measuring your average off-bottom torque friction factor, you're getting pretty close. And I can say that with confidence because we've had several wells with downhole weight, downhole torque sensors where we compare this methodology to what we actually measure, and they're spot on. We're right there. In fact, back in my K&M days, we published a paper, an SP paper, where we talked about that. So it's an effective method. It's certainly close enough for government work. If you're trying to get to the third decimal point, then it's not good enough. But for solving that sort of problem, it's certainly good enough.
All right. So this kind of goes back to what he just had, recommendations to get better data points to more accurately calibrate torque and drag. So we were just kind of talking about the pickup and slack off there. But anything else you want to add to that?
Yeah, I will leave that to Devi to talk about. And if we find that there's anything that Devi didn't cover, we'll cover it in episode 8.
And Devi will be doing episode 7. So be sure to tune in then. Carlos said here was the SPE paper. I'm not sure which one that might have been referencing because we've talked about a handful of different
That's probably
things.
the shiv friction one.
Yeah. All right. Let me jump over to this one because I can answer this one. Hello, David. Will there be a replay of this video? Yes. So all of these episodes, if you guys didn't hear me earlier, will all be going to YouTube. You can watch them on LinkedIn and still be able to see all of the comment section, right? We'll make a link in my profile so you can go there and it'll be one of the featured something or others there. So we'll have them all there. The easiest way, the quickest way to probably be able to find them will be on YouTube. The only issue there is you won't see all of the LinkedIn commentary that kind of takes place because the majority of people I've been watching here, I think we hit probably 260 or something on LinkedIn, probably about 60 or 70 people watching on YouTube. So that just kind of depends there. It'll also be on Facebook where there probably were no comments, but you can also watch it there. So LinkedIn, YouTube, and Facebook, all of it there after the fact. Okay. So let's ask this one, and I think we got one other, maybe two others, and then we'll call it a day. Then we'll go. Somehow air drilling have high ROP with very low weight on bits. How is that correlated with high friction factors? Or maybe this is just applicable on highly deviated wells.
Yeah, you don't see very many highly deviated wells drilled with air. In vertical wells, friction doesn't really prevent you from drilling fast, even if you've got super high friction factors, because if you've got very little normal force, even if you have very high coefficients of friction or friction factors, it doesn't really change anything. You're still multiplying by a very small number. There is a physics reason why you can drill very fast with air. I won't open that can of worms, but just say if you've watched any of Fred DePriest's talks on MSE, he covers that quite well, and we could talk about it offline if anyone's interested, but it's not topical to this.
There's a good comment. Soft string with bending stress magnification is better for model for big hole size, deviated well, or stiff string. Actually,
yeah, 99% of what I do is soft string with bending stress magnification.
There you go. And then Cody says, can't wait to dive into more details on friction reducing devices, more specifically mechanical versus mud based.
We are going to talk about that with Dr. Snow, with Mitch, right?
Yeah. And so Cody's actually with WWT, so they'll be sponsoring that episode. Perfect. But today is sponsored by NEWPARK, so thank you to NEWPARK. This one just says, or use a continuous circulation system.
Somebody's trolling me. Somebody's trolling.
Oh.
That's another, yeah, well.
Okay.
We'll get into that.
Last question for the day. There we go. What is the effect of bending stress magnification on torque and drag simulation?
We
think a good one to end on.
Yeah, we don't have enough time to cover that today. I think it is coming up in the next one. Oliasov should cover it. But again, there's another SP paper, some guys at Shell really do a great job of outlining the math of figuring out how much, what bending stress magnification means is, so suppose that you've got a dogleg curvature, right? I got to move this window so I can, yeah. So let's say you've got curvature and you have a joint of pipe, drill pipe with tool joints that goes across that curvature. The bending stress that you would calculate just from the dogleg is not really what happens. You get this amplification effect because there's shear stresses that happen close to the tool joints, because it's not just a uniform diameter wet noodle that goes around the curve. You've got tool joints, and if there's enough bending, the tube in between the mid span of the tool joints touches the hole, further amplifying the shear stresses near the tool, not at the tool joint, but near the tool joint. And there's a good, again, I'll reference this on LinkedIn afterwards, SP paper that outlines how to do that.
All right. Okay. So to wrap up, first and foremost, thank you, Brandon, so much for taking part in this. As said here in the latest comment, thanks David Gibson and Brandon Foster for this free class. It saved a couple of dollars for my company. Just joking, it was great. I think everybody saved their organization quite a bit of money. Special thanks to NEWPARK for being able to sponsor this one. We really do appreciate that. If you guys are interested in the upcoming ones, so here's a couple of things that I'm going to request. Right, follow me and Brandon on LinkedIn. Follow our future presenters and companies on LinkedIn. Tag somebody in the comment section here to be able to let them know about this, right? If you've got anybody else that you work alongside, a coworker, if you've got any value out of this and you're still watching, you're one of the, out of 150 people that are still watching this, please tag somebody in the comment section. Just write a comment. That helps with the LinkedIn algorithm, right? It can just be on the keyboard and then press enter. Strangely enough, it helps, right? Follow me, follow Brandon, follow for the future ones. Oh, and send out invites, right? So we've got the main one that's got about 15,000 people attending. Invite some other people to be able to come along to the next ones. The thing that really pushes this forward and makes this possible to be able to continue doing these is people actually tuning in, people watching, people engaging with the content that we're putting out there. If nobody watches, nobody engages, nobody talks about it, then this becomes the end of a series, right? And then we have to think of something else to be able to shock and awe people into this. So once again, Brandon, thank you so much, man. I really, 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 really do appreciate it. And for everybody that is still watching, please write a comment, a nice little thank you to Brandon. And we will get the PowerPoint presentation posted on Thursday. And we'll also start to give you guys some more information about what episode 8 is going to be. So if you've got any thoughts, any ideas, anything that we've missed, be sure to put those in there. So Brandon, any last thoughts from you?
No, thank you for having me. Thank you to everybody that attended and had questions to ask. This is a lot of fun. And it takes somebody like you with the vision to do this. Joe Rogan of the oil field. So thank you.
I'll take it. All right. So everybody saying thanks. Okay. There's somebody's name. Great learning in bit. Oh yeah, we're getting some people tagged in here. Awesome. Over here it says thank you. Interesting show. All right, guys. Once again, thank you all so much for taking part in this. This is just, there's been so much work behind the scenes to be able to get to just today. And there's so much more work, so many learnings that we're taking from this to be able to put everything together. If you've got questions that were not answered, write them down, put them down, get them ready, bring them back. Let's start feeding those back to us for episode 8, because episode 8 has not been written yet. So if there's anything in there that we don't get covered, if it does get covered, one of the other weeks, we scratch it off the list. But anything new that we need to be able to cover in episode 8, we'll make sure it's there. And Brandon will be back, and we'll find another sponsor for that one. And to Dane, we'll be sending you out your drill bit here pretty soon. And maybe we'll even send you over there one too, Brandon, so you have something nice to put on your thing back there. And just so you know, my very first vehicle was a 1984 Chevy Blazer, so I know everything. I know everything that you're going through with that vehicle. So
know way more about that than I want to.
Yeah. All right, guys. Thank you all so much. We really, really do appreciate it. Once again, like, share, subscribe, hit the notification bell if you want to be able to get notified of these upcoming ones. And as I always say, know your industry.